Now, in case of Frenkel defect, what you find is that, now one thing let me tell you, you have understood a little bit now that Schottky defect is similar to vacancy defect. And now you will see that Frenkel defect is similar to interstitial defect. You will see it now. Frenkel defect is what? If an ion is missing from the lattice side, causing a vacancy or a hole there, it is missing from the lattice side. These are the lattice side. They are known as lattice point. Okay, it is missing from the lattice side. Got it? Causing a vacancy or a hole there. A hole will be created. Got it? But it occupies the interstitial side. It is being missing from here and it will occupy the interstitial side. I told you, no? It is similar to interstitial defect. It will occupy the interstitial side. Got it? Thus maintaining the electrical neutrality of the substance. Got it? As well as the stoichiometry of the substance. Because stoichiometry is also not disturbed. Stoichiometry means the ratio between the cations and anions is also not disturbed. Because an atom is missing from here and it is occupying the interstitial side. Let us say this cation is missing from here. And it occupies the interstitial side here. That is. Okay? So hence, this type of defect is known as what? This is called as Frenkel defect. Very simple. Similar to its interstitial defect. So what you find is that the electrical neutrality is also maintained, as well as the stoichiometry of the solid is also being maintained. So this is known as Frenkel defect. Okay, fine. Now what are the conditions then for Frenkel defect? As in Schottky defect, what you have seen? High coordination number. It will be here low coordination number. That is, a coordination number will be either 4, 6, we can say that. Clear? Or 8 also can be in certain cases. And there should be a large difference in the size of cations and anions. There you have seen small difference. For that reason I gave you the for example NaCl, KCl, KBr, AgBr, or CSCl, LiF. I told you the example. Here there should be large difference in the size of cations and anions. So large difference means here it can be AgCl, it can be AgBr, it can be AgI, mainly silver salts. It can be ZNS, mainly silver salts, you can say that. So one thing you see, you note it here, that AgBr I have said both. In both I have said, that is Schottky as well as Frenkel. So remember it, AgBr is a solid which shows both Schottky defect as well as Frenkel defect. Very, very important this one. It is coming under both Schottky as well as Frenkel defect. But one more thing, remember it. Frenkel defect is not being shown by alkali metal atoms. Why? Because the size of the alkali metal atoms is bigger. You know that. You have read it in periodic table. The atomic size decreases from left to right. And alkali means group 1. The atomic size is the bigger. So, if it is bigger, how it will occupy the interstitial site? How it will occupy the interstitial site? Because atomic size is bigger. Clear? So, hence, Frenkel defect is not shown by alkali metal atoms. That is NaCl, KCl and all these things. They do not show the Frenkel defect. Because if an alkali metal ion will be missing from the lattice side, it will not occupy the interstitial side, because the size of the atom is so big that it cannot occupy the space which is created by the metal atoms. When the metal atoms are arranged in the lattice sides, the space which is being created, the hole which is created, the interstitials is created, whatever you can say, it is not going to occupy in that particular, what you can say, space. So hence it is not shown by alkali metal atoms. Got it? Frenkel defect. I gave you the reason also that why it is not being shown. Alright, so in this way you understood the stoichiometric defect, that is your Schottky defect, and the Frenkel defect. Just opposite, remember. In Schottky, equal number of cations and anions are missing from the lattice side, so that electrical neutrality is maintained. And it is shown by high coordination number and small difference in the size of cations and anions. Alright, here it is the cations are missing from the lattice side, but it occupies the interstitial side. But it is not shown by alkali metal atoms. Why? Because they are bigger in size. It cannot occupy the space which is created by the interstitials. Got it? It's a small one, it cannot occupy that. So AgBr is a kind of solid which is shown both by Schottky and Frenkel. And the next is that if you see the conditions for the Frenkel defect, it is opposite to that of Schottky defect. In Frenkel defect, there should be low coordination number and there should be a large difference in the size of cations and anions. Okay, this is very important. Schottky and Frenkel you understood. So hence you understood also stoichiometric defect. Now we will come to the non-stoichiometric defect. We can say that non-stoichiometric defect. We will come to it. So under point defect only it comes. The first one we have discussed with you. The second one, the non-stoichiometric defect, I should say. Now non-stoichiometric defect we are having, that is metal excess defect and metal deficiency defect. We can say that. Clear? What I said? One is your Let me write here so that I'll get the space. Metal excess, and another is your metal deficiency. Metal excess defect and metal deficiency defect, we can say that. Okay. Now metal excess defect again is of two types. It is being shown by anion vacancies. Definitely, if anion will be less, cations will be more. So hence, metals means basically they are cations, positive charge. Or we can say under metal excess, anion vacancies we can say, or we can say that is addition of extra cations on the interstitial side. Alright, addition of extra cation. That also is metal excess, addition of extra cation. If I add some cations, then the metal will be increasing, isn't it? Because I said, metals are basically positive charge, they are cations. So addition of extra cations. Where I am going to add it? In the interstitial side I am going to add it, the extra cations, the addition of extra cations which I am going to add it in the interstitial side. Now how we will understand this particular one? The first one is your anion vacancies. The first one is anion vacancies. Now what do you mean by anion vacancies? Now see here, what you need to do is here is that you will be heating a particular solid. Alright, let us say we have taken sodium chloride solid, we have taken it, and we will be heating in presence of sodium vapor. We will be heating in presence of sodium vapors of sodium. We will be heating sodium chloride in sodium vapor. So when you will be heating what you can say sodium chloride in sodium vapor, let us say here we are having, that is sodium chloride, you can see it here, NaCl, we are having Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. You will be heating, that is in presence of sodium. Excess of sodium will be there. Now this sodium, what it will do is that it will pull, it will have a nature to pull the chloride ions towards itself. Definitely. So when that sodium is going to pull the chloride ions towards itself, now sodium cannot pull because sodium is neutral. How it will pull? So it needs to be converted into a cation. So how it will get converted into cation? Sodium will lose an electron and it will form sodium ion, and hence this sodium ion will now pull the chloride ions towards itself. This sodium ion, understood from where you got this particular sodium? We have heated sodium chloride in sodium vapor. Now sodium vapor, that sodium atom, alright, it's going to pull the chloride ions towards itself. Now sodium atom cannot pull the chloride ion because sodium atom is neutral. Alright, it has to be converted into cation. So how it will get converted into cation? It will lose an electron, it will get converted into cation. So this sodium ion can pull the chloride ion. Let us say it pulls this chloride ions towards itself. So vacancy is created or not? What vacancy is created? An ion is going, so anion vacancy is created. In that particular, what you can say vacancy, E minus comes and takes its place. E minus. The sodium loses that electron. This goes and take the place of that particular, what you can say, anion. Because anions are negative, electrons are also negative. No problem. So the electron goes and takes the place of that particular anion vacancies. Got it? So by this electrical neutrality of the solid is maintained. Now what is going to happen? When the light falls upon this particular, what you can say, the sodium chloride crystal which is heated in sodium vapor, these electrons, listen carefully, these electrons, alright, just one electron I am showing you, it can be so many electrons it can be, isn't it? So these electrons pulls, that is, it pulls, I am saying, it absorbs energy from the light. Why it is going to absorb? Because these electrons, charged particle, it is going to absorb the energy towards itself. Alright, so when it is going to absorb the energy towards itself, the light which will be absorbed by this particular electrons, got it, when it will strike this particular surface, it is going to, some of the light is going to get absorbed, some of the energy, not the entire energy. Remaining energy or the remaining light will be coming out from the surface of this particular sodium chloride. So that is nothing but what light? Deficient light will be coming out from it. So what the color you will see then? You will see that is nothing but, in case of sodium chloride, you will be seeing it is be yellow color. Why? Because when sodium is heated, it gives you what? Golden yellow color. Now you will say, sir, if potassium chloride, if I take, what will happen? It will give you purple color, crimson color, violet color it will give you, because you know potassium ions imparts violet color to the flame. You have read the flame test. You will say, sir, if I take calcium chloride, what will happen? Red color, because calcium ions gives brick red color to the flame. So whichever substance you are taking it, that particular color you will be getting it. Understood how that color is coming from? Because when the light falls upon this particular electrons, now let me tell you, a name is there for this particular what you can say, this region. This called is F center. This is known as F. F has come from the German word Faber, F-A-B-R-E, Faber. Got it? You have heard now? Faber-Castell company which produces colors. Got it? From there only we have got it. That is Faber, F-A-B-R-E. It is from the German word. In German word, Faber means color. Got it? So this is known as color center. This particular center is called color center. I explained to you how it is color. Once more I am saying you. When the light falls upon this particular one, as it is charged particle, it is going to pull, it is going to absorb some energy towards itself. So the remaining light will be reflected from the surface of the sodium chloride. Remaining energy which will be given out. So that particular energy will be which color? It is yellow colored. Why? Because sodium imparts golden yellow color to the flame. If it is potassium chloride I would have taken, then you would have got, that is violet color or crimson color, whatever you can say that, or purple color, whatever you can like, you can say. Next, if I take calcium, you would have got nothing but, that is reddish red color you would have got. Suppose if I have taken strontium, I would have got green color. In this way you know it, that different metals, alkali metals gives different color to the flame. Alright, so this particular defect is known as anion vacancies. This particular, it is coming under metal excess defect. How you know it is metal excess defect? Because when the sodium ions pull the chloride ions towards itself, you can see a vacancy is created. By vacancy is created by what? By loss of anions. And in that particular space, this electron comes and takes its space, due to which electrical neutrality is maintained. No doubt about it. Electrical neutrality is maintained, but it imparts color. That particular region imparts color. So hence it is known as F center, which is otherwise called as colored center. I hope you got it. This one, this particular one. It's very, very important. This one, it comes in your reasoning question, my dear students. Reasoning question it comes. So hence you need to understand well, and also at the same time you need to write it down in your notebook. Alright, if you don't write, you will not be able to write in your exams. Next is under metal excess, another one is there, addition of extra cations. Now, you know that zinc oxide, it is yellow when hot and white when cold. You have studied in lower classes. It is yellow when hot and white when cold. Why? Because you see, when zinc oxide is heated, it gives Zn2 plus ions plus half a molecule of oxygen is given out, because O, single atom. So we will write half a molecule. Now to maintain the electrical neutrality, got it? 2 electrons also will be gained. So 2e minus, plus into minus, minus 2, plus 2, neutral, because ultimately the product is neutral, the reaction has to be, equation has to be balanced, so it is balanced, you can say that. See, Zn2 plus, and it loses 2 electrons, and this oxygen. Now this oxygen is being lost into the atmosphere. Got it? When oxygen is lost, then what remains behind? The zinc ions is remaining behind. So zinc ion, where it will go? It will occupy the interstitial sites. Got it? And hence that particular is known as addition of extra cations to the interstitial site. Now interstitial site means, you might be wondering, what is interstitial site here? See here. See. Okay, this is your zinc ions, this is your O2 minus. This is your zinc ions, this is O2 minus. Again zinc ions and O2 minus. Now what you find is that when zinc oxide is heated, this zinc, what you find is that Zn2 plus, it occupies the interstitial sites. This zinc ions, because oxygen gas is released, you can see half O2, it is released. It is released in the atmosphere. So the cation is left behind. That cation occupies the interstitial site, and this electron occupies the neighboring interstitial site. The electrons occupies, due to which electrical neutrality is maintained. Minus 2 plus 2, balanced, neutral. Due to which electrical neutrality is maintained. Due to this reason only, zinc oxide, you know, it's a physical change. Zinc oxide, when it's heated, it's yellow when hot, and white when cold. Why white when cold? Because zinc ions, from wherever it is lost, it comes back to its original place, and it gains oxygen from the air. So hence it is yellow when hot and white when cold, because when you are heating it, it loses the zinc ions, and this zinc goes and occupies interstitial site. When you are cooling it, this zinc again goes back to the, what is that? The lattice site, and oxygen it gains from the air. That's it. In this way, what you find is that this particular defect is otherwise known as metal excess defect. Yes, excess of metal. But where this occupies, it occupies as cations in the interstitial sites. So this defect is coming under non-stoichiometric defect. We can say that. Okay, thank you.